NetSim use case: designing a nationwide network connecting universities, analyzing capacity, latency, and the impact of link failure. Network design: 6 cities in Switzerland: Basel, Bern, Fribourg, Lausanne, Luzern, and Zurich. Each city hosts a router and a server, interconnected with 10 megabits per second links. Traffic configuration: bidirectional traffic flows between all city pairs, totaling 30 flows. Analysis: analyzing how increasing data traffic rates between cities affects network performance, particularly throughput and latency. Focus on OSPF convergence: understanding how quickly OSPF recalculates routes and restores network stability. Examining network resilience by assessing OSPF's ability to reroute traffic effectively during link failures and studying the impact on throughput and latency. Here we have the Switch LAN network, which connects major Swiss universities and research institutions through high-speed links, allowing them to communicate. Our goal is to model and analyze this network in NetSim. A network scenario is designed to connect universities across 6 cities, with each city equipped with 1 router and 1 server. This setup is implemented in NetSim, where every link between cities has a capacity of 10 megabits per second. The traffic flow is configured to flow between all city pairs. Since we have 6 cities in this network, each city establishes traffic flows with 5 other cities. This results in a total of 6 times 5, or 30 traffic flows. We now move to the Your Work menu in NetSim, which displays the imported experiments. These files are available in the link provided in the video description. We have 3 scenarios prepared for this simulation. Each case examines a different aspect of the network's performance and resilience. In case 1, we've set the traffic rate for each flow to 1.9 megabits per second. This rate is chosen because each city exchanges traffic with 5 other cities through a bottleneck link that connects the router to a server. With each link capped at 10 megabits per second, the bottleneck rate per flow comes out to approximately 2 megabits per second, 10 megabits per second divided by 5 flows. In the router properties, we will first configure OSPF as the routing protocol. Next, we move to the application properties. Here, each flow is set to a rate of 1.9 megabits per second. But how do we arrive at this value? Let me explain the calculation process. The generation rate is calculated using the following formula. Generation rate equals packet size into 8 divided by interarrival time. Now, let's substitute the given values into this formula. Packet size equals 1,460 bytes. Interarrival time equals 6,147 microseconds. When we plug these values into the formula, the calculation becomes generation rate equals 1460 into 8 divided by 6147. Solving this gives approximately 1.9 megabits per second, which matches the configured flow rate for each application. Finally, in the configuration reports, we enable throughput and latency plots in the plot section to monitor performance. The simulation runs for 50 seconds. In the application metrics, for Lausanne to Zurich case, we observe that the packets generated total 7,978. Packets received are 7922, and the obtained throughput is 1.85 megabits per second. The small difference is due to the packet errors in the link. Here is the throughput versus time plot for traffic flowing from Lausanne to Zurich, and this one shows the throughput versus time for traffic from Zurich to Lausanne. The variation in throughput occurs because we are generating a variable bitrate traffic with an average rate of 1.9 megabits per second. Here, we have 2 delay versus time plots. The first plot shows the delay for traffic from Lausanne to Zurich servers, while the second plot represents the delay from Zurich to Lausanne. In both cases, we can observe that the average latency fluctuates around a stable mean rather than increasing continuously. This indicates that the network is effectively handling traffic in both directions, maintaining smooth performance between these endpoints. Now, let's look at the OSPF convergence time in our network. OSPF convergence is the time it takes for routers to update their tables and begin accurately forwarding data packets after establishing connections. In our packet trace, we can see that OSPF hello packets are exchanged initially between the routers. These hello messages are essential for routers to discover each other and establish neighbor relationships. Once the hello packets are exchanged, the routers update their routing tables, and we can observe the first data packets being forwarded at around 1217 microseconds, or 1.2 milliseconds. This moment marks the OSPF convergence time. In summary, the convergence time of 1.2 milliseconds means that within this period, all routers have successfully updated their tables and established the best paths for data packets. Now, let's explore what happens when we push the network closer to its capacity. We're using the same 10 megabits per second wired link speed, but with a higher traffic rate of 1.95 megabits per second. We analyze its effect on the network. The simulation runs for 50 seconds. Here, in the application metric for Lausanne to Zurich, we can see throughput for this flow is 1.869 megabits per second, which is slightly below the generation rate of 1.95 megabits per second. If we look closer, a total of 8,193 packets were generated, out of which 8,005 packets were successfully received, confirming some packet loss. In the throughput plots for traffic between Lausanne and Zurich, we observe that the application throughput remains steady, close to the generation rate of 1.95 megabits per second, but falls just short. This indicates that some packets may be delayed or dropped as the network approaches saturation. Now, let's examine latency over time. In both directions, from Lausanne to Zurich and Zurich to Lausanne, we see a gradual increase in latency. This rising latency suggests queuing delays, a clear indication that the network cannot fully handle the increased traffic rate of 1.95 megabits per second without congestion. From these results, we can infer that saturation occurs somewhere between 1.9 and 1.95 megabits per second. In case 3, we're examining the impact of a link failure on overall network performance. We are simulating the failure of the Basel-Zurich link in this scenario. To configure this in NetSim, we click on the Basel-Zurich link, which opens the link properties window on the right-hand side. Then, we expand the link section, followed by the medium properties, and finally, under link failure, we set the downtime to 10 seconds to simulate the failure at the desired time. In the throughput plots for traffic from Lausanne to Zurich and Zurich to Lausanne before the link failure, throughput is stable at around 1.9 megabits per second, close to the generation rate. However, after the 10-second mark, when the Basel-Zurich link fails, throughput drops significantly to around 1.2 megabits per second. This decrease occurs because traffic is rerouted over alternative paths, which increases congestion across the network. Now, let's examine the latency between Lausanne to Zurich and Zurich to Lausanne after the link failure. Latency is about 51 milliseconds. However, once the Basel-Zurich link fails, latency spikes drastically, reaching an average of 7 seconds. This surge is due to rerouting, which increases travel time as data packets take alternative paths. Next, we analyze the traffic directly affected by the Basel-Zurich link failure. In the throughput versus time plot for Basel to Zurich, we see a similar pattern. Throughput drops sharply after the 10-second mark as the direct link is no longer available and traffic is rerouted. Looking at the latency versus time plot for Basel to Zurich, we notice that latency increases from an average of 61 milliseconds. Post 10th second, the average delay shoots up to 7 seconds. Thanks for watching.